Welcome to the debate. Today, we are asking a pretty radical question. Have modern software architects completely forgotten the laws of physics?
Right. Or, maybe we've just decided we don't need them anymore.
Well, that is exactly what we are looking at today. We're diving into the Temporal think tank archives, which is a specific episode from the series, Decoding the Pillars of History. And the premise is honestly striking. It asks whether modern cloud architecture and system design fundamentally lack the geometric efficiency of ancient grids.
Yeah, it really zeroes in on this idea of superimposing classical engineering logic, what the ancients called techne, to sort of, cure the bloated, fragile complexities we deal with in the 21st century.
Exactly. Or on the flip side, does the modern web actually require this disposable chaos just to function? And, for our audience, if you are a senior systems engineer or, say, a technical founder listening to the show, you are probably rolling your eyes right now.
Oh, guaranteed. The idea of applying Roman masonry or ancient aqueducts to your agile software sprints sounds a bit absurd at first glance.
Right, but we aren't talking about piling literal limestone here. We are debating the fundamental structural logic behind systems architecture, data flow, load balancing, and even corporate scaling. The core argument is whether we've traded structural integrity for the mere illusion of speed. And I am taking the position that we absolutely have.
Okay, and I'll be defending modernity here. But go ahead, lay out your case.
Well, I argue that modern engineering has severely lost its way by basically abandoning its foundational logic. The classical approach to mechanics wasn't restricted by physical materials, like bronze or stone. It was rooted in an absolute adherence to logic, spatial optimization, and permanence.
Right.
By treating data like physical mass and applying the philosophies of classical visionaries, I think we can dismantle modern technical friction entirely. We can build digital infrastructure that operates flawlessly under massive weight.
That sounds incredibly appealing as a philosophical thought experiment, I'll admit, but I argue that it fundamentally misunderstands the demands of modern scaling. The bloated complexities that we complain about in 21st century systems, rapid iteration in software, auto-scaling environments, synthetic integration in hardware, they aren't failures of logic.
They certainly act like failures sometimes.
Sure, but they are necessary adaptations to a hyper-connected, constantly evolving global landscape. Rigid, monumental permanence is actually the enemy of agile innovation.
Well, then let's test the durability of modern agility by looking at data flow. The Temporal think tank archives feature Hero of Alexandria. Hero was essentially the ancient world's master of automation, right?
Yeah, the pneumatic engines, the programmable theaters.
Exactly. His entire engineering philosophy was based on event-driven pneumatics. Action only occurs when physical pressure necessitates it. So the archives hand Hero a bloated modern web application to diagnose. Specifically, they look at an educational student testing platform built with a React front-end and a Python-based fast API backend.
Pretty standard stack for an edtech platform, really. But you're about to tell me it's built completely wrong.
Oh, it frequently crashes under its own weight. Because think about the mechanics of an online final exam platform. It has to maintain synchronized browser focus parameters to ensure, the student isn't clicking into another tab to cheat.
Right.
While simultaneously running automated integrity flags on the back end. Now, in our modern paradigm, this results in relentless asynchronous polling. The React client constantly interrogates the server. Are we still focused? Did a flag trip? Are we still focused?
60 times a minute, thousands of students at once.
Yes. It leads to timeouts, database locking, and browser freezing. It's a mess. Hero wouldn't see a coding error here. He would see a massive failure of mechanical plumbing. He would see a system wasting immense kinetic energy just to ask a question.
Wait, but pneumatic systems operate in a closed, highly controlled environment. Modern cloud architecture is anything but closed. Hero's solution works beautifully in an isolated theater, sure, but not across a massive distributed network.
But the physics of his solution still apply perfectly. Hero would treat those fast API endpoints like physical mechanical valves. He would eliminate the bloated polling entirely and replace it with WebSockets, pushing state changes only when triggered by an actual event.
So moving to a purely push-based state.
Exactly. If the student's cursor leaves the window, a flag trips and the valve opens. Otherwise, the system rests. It creates a single source of truth, completely closed hydraulic loop. A single, elegant input triggers a flawless mechanical output, instantly reactive, without ever lagging the browser. It literally proves our modern synchronous processing demands are built on highly inefficient friction.
I mean, the elegance of a closed hydraulic loop is undeniable when the pipes never leak. But let's talk about the reality of the environment here. A strictly event-driven pneumatic architecture relies on perfect network stability. WebSockets require persistent connections.
Sure, but
Hold on, if you have 10,000 students taking an exam on fluctuating rural Wi-Fi networks, those persistent connections are going to drop. And when they drop, the server has to manage the overhead of constantly re-establishing the handshake over and over. Suddenly, your elegant hydraulic loop is just spraying water everywhere.
A dropped connection is a network degradation issue, though. It's not a flaw in the application's structural logic.
But the structural logic has to survive the environment it lives in. Modern synchronous processing, even with its so-called bloated polling, provides a vital layer of stateless flexibility.
But at what cost?
Well, look, if a request drops in a polling architecture, the system doesn't panic. The next request simply picks up the slack 3 seconds later. It doesn't require maintaining a fragile, continuous pneumatic pressure across a massive, unstable cloud environment. This is exactly why I argue for modernity. A strictly event-driven architecture simply does not scale reliably when the state changes are happening across a chaotic global network rather than, a neat Alexandrian workshop.
okay, but even if you optimize the code to accommodate a chaotic network, none of it matters if the physical servers hosting that code collapse under the payload weight. We have to move from the logic of the software to the physics of the server itself. And this brings us to Archimedes of Syracuse.
Right, the concept of leverage applied to server space.
Yes. Archimedes proved that with a long enough lever and a solid fulcrum, you can move any mass with minimal effort. In our world, the mass that engineers manage is data bandwidth and API transaction payloads.
Okay.
So let's apply Archimedes to a heavy 3-tier stripe transaction system. Today, when faced with high user traffic and massive webhook payloads, the standard unoptimized deployment treats it as a brute force problem. If traffic spikes, we just auto-scale. We purchase massive, expensive server compute just to keep the system from collapsing.
Right, just throwing more virtual machines at the problem to absorb the hit.
Which is the exact opposite of engineering. It's just outspending the friction. Archimedes applies the laws of physical leverage directly to network traffic. He looks at a content delivery network like Cloudflare, and he doesn't just see a security perimeter or a basic cache. He sees an absolute digital fulcrum.
Ah, I see where you're going with this.
The lever is distance. By pushing the cache and the edge compute logic to the physical edge of the network, closest to the user, he lengthens the lever. So when those heavy cryptographic Stripe webhooks hit the system, the origin server barely has to lift a finger. The mathematical distribution of that traffic displaces the weight flawlessly across a distributed backend, like, say, Railway.
Wow.
He balances the webhooks with absolute precision, proving you don't need infinite bloated compute power if you engineer perfect leverage.
Okay, I understand the physics metaphor, and it's clever, but treating network traffic purely as static physical mass is, well, it's reductive. Data bandwidth isn't a block of marble resting on a lever. Network traffic fluctuates instantly and asymmetrically.
But the principles of load balancing still mathematically mimic a fulcrum, regardless of how fast that mass fluctuates.
To a degree, yes. Edge computing does act as a lever, but Archimedes' physical lever requires predictable mass. A massive DDoS attack or a sudden localized viral spike in mobile traffic, that behaves more like a chaotic fluid dynamic than a solid object.
But a fulcrum handles fluid weight if balanced correctly.
While a CDN acts as a fulcrum, the modern abstraction of serverless architecture and auto-scaling, the very things you just dismissed as throwing money at the problem, are actually what allow us to dynamically generate new levers out of thin air, exactly when and where they are needed. We aren't just moving a static boulder here. We are dealing with an Earth that changes its mass, density, and location every single millisecond. Static leverage snaps under chaotic pressure.
You consistently return to this idea that the modern digital world is inherently chaotic, and therefore we must build flexible, abstract, and even messy solutions to survive it.
Because it is.
Well, that brings us to a major question raised by the Temporal think tank. Does modern cloud architecture truly lack the geometric efficiency of ancient grids? Let's look at how we store the chaotic data you're describing through the lens of Hippodamus of Miletus.
Right, Hippodamus. He pioneered urban grid planning in antiquity. He basically took sprawling, disease-prone organic settlements and enforced a rigid mathematical zoning structure onto the streets.
Exactly. And the modern equivalent of a sprawling, chaotic ancient city is the administrative nightmare of disorganized databases. The archives outline a specific scenario here: an educational administration system tracking localized files, iterative student self-assessments, and cross-departmental grading metrics.
Sounds like a headache.
Oh, it is. When administrators manage this without structural discipline, the system descends into total chaos. Corrupted file uploads overwrite older versions, late submissions sit in unmapped directories, and calculating a simple campus-wide progress report becomes this labyrinthine nightmare.
So Hippodamus steps in to zone the data structure.
He enforces absolute geometric order. He treats the relational database like a city map, aligning every single metric into a perfect, navigable, unalterable grid. Essentially, a strict SQL schema.
But he goes even further. To maintain this geometry, he drafts ironclad notices.
Which are what exactly? These are the rigid civic laws of his digital metropolis. If a student upload doesn't meet the exact schema requirements, the database forcefully rejects it. There is no flexible schema on read compromise. By enforcing this strict geometric system, generating a progress report isn't a chaotic hunt through folders anymore. It is a matter of absolute certainty. He guarantees a system that is transparent, instantly queryable, and utterly immune to administrative collapse. Rigid order solves chaos far better than flexible abstraction.
Okay, but if Hippodamus's grid is the ultimate relational database, perfectly zoned, mathematically aligned with rows and columns, you are completely ignoring that the modern world is increasingly reliant on the exact opposite. We depend on the sprawling, chaotic city of unstructured NoSQL data for a very good reason.
Wait, you are actually defending disorganized, schemaless data lakes as a positive architectural choice?
I am defending it as a necessary evolution. Look, strict, unalterable geometric grids are brilliant for localized, highly structured data, a gradebook or a financial ledger, sure. But modern tech operates on massive, varied data inputs that absolutely cannot be predicted.
Such as?
Think about IoT sensor logs on a manufacturing floor, or real-time machine learning training data, or highly asymmetrical social media inputs. These data types don't fit into right-angled relational tables without stripping away all their context.
But if you don't enforce a schema before the data is written, you are just dumping garbage into a void. You can't query it reliably later on.
You query it by applying the schema when you read the data rather than when you write it. The modern NoSQL database is a sprawling city, yes, but allows for rapid organic growth. If you force modern unstructured data into a rigid Hippodamian grid, you lose the nuance, the edge cases, and all the relational metadata that just doesn't fit into your neat little boxes. Chaos in a data lake is a feature of massive scale. It's not a failure of administration.
I disagree completely. Allowing data to sprawl without an enforced foundation isn't a feature. It's just deferring the collapse to the data scientists who have to clean it all up later. Which transitions us perfectly, actually, from digital foundations to the structural foundations of the tech industry itself.
All right, where are we going with this?
Let's apply this ancient logic to how businesses scale and how physical hardware is built. We have to talk about Imhotep,
The architect of the step pyramid of Djoser.
the man who understood a profound, unyielding truth. To build upward into the sky, you must first lay an impossibly wide, flawless, and heavy foundation. The stability of the peak is entirely mathematically dependent on the integrity of the base layer.
Now superimpose Imhotep onto modern startup culture and venture capital pitches.
Oh boy.
Modern founders prioritize rapid scaling, aesthetic marketing, and aggressive upper-tier user acquisition. They desperately want to build the peak of the pyramid while entirely neglecting the base.
You're referring to startups prioritizing growth over immediate profitability.
Exactly. Imhotep would view their business pitches as fundamentally flawed masonry. He would throw out all the tech buzzwords and implement a strict, multi-tiered scoring rule system for venture capital. In this architectural metaphor, the base of the pyramid is unit economics. The middle tiers are supply chain logistics and market capture, and the peak is user acquisition scaling.
Okay, I follow the structure.
Imhotep demands that before a founder is allowed to spend a single dollar on scaling the peak, the base layer of unit economics must be mathematically flawless. If the cost to acquire a customer is higher than their lifetime value, the base cannot physically support the weight of the upper tiers.
And the whole thing comes down.
The venture collapses under its own economic weight. Imhotep demands that business plans be built out of indestructible mathematics, not speculative venture capital sand.
I mean, the step pyramid has lasted for millennia. It's an imposing visual, I'll give you that. But demanding that a venture plan be built out of stone before you are allowed to scale is a death sentence in the 21st century tech sector.
Wait, ensuring a mathematically flawless foundation of unit economics guarantees survival. How on earth is that a death sentence?
Because the ground underneath the startup shifts every single day. Imhotep's demand for a massive, unbreakable base entirely prevents agile pivoting. Let's say you spend 2 years architecting an unyielding foundation of market research, perfectly zoned supply chains, and rigid capital allocation.
A solid business.
Sure, but by the time you lay the final stone of that base, a competitor releases an open-source AI model that renders your entire product obsolete overnight.
So your solution is to build a flimsy company instead.
My solution is to acknowledge that modern startups don't build out of stone because stone cannot pivot. They build with scaffolding. It looks flimsy to an ancient Egyptian architect, sure, but scaffolding can be torn down, moved, and rebuilt in a single week to chase where the market actually is. You figure out the exact unit economics while you scale, because if you wait for the perfect foundation, the market just leaves you behind.
But scaffolding inevitably crashes down on the consumer when the company scales too fast and the product breaks.
Not if you manage it right.
Let's push this exact philosophy into the physical world then, onto the consumer hardware that actually runs our lives. We've discussed software, we've discussed data, and business strategy. Now let's look at the absolute plague of planned obsolescence through the eyes of Apollodorus of Damascus.
Okay, the chief architect for Emperor Trajan, responsible for monumental structures like Trajan's Bridge over the Danube.
A man who engineered infrastructure to dominate harsh environments for centuries. Hand Apollodorus a maintenance quote for a modern consumer vehicle that has just hit 100,000 kilometers.
I'm sure he'd be thrilled.
The quote details the wholesale replacement of fragile, integrated synthetic components. We're talking sealed suspension struts, computerized subassemblies, a disposable plastic unibody chassis. The modern manufacturing paradigm dictates that requiring a massive structural overhaul at 100,000 kilometers is just standard wear and tear. Apollodorus would be viscerally disgusted.
Disgusted?
Yes. To a Roman engineer, a machine failing at that distance is a humiliating failure of design.
Well, to be fair, the Romans were engineering stone to sit stationary, or bridges to hold marching legions. We are talking about complex, kinetic machines with thousands of moving synthetic parts.
The complexity of the machine doesn't excuse the underlying philosophy of disposability, though. Apollodorus would reject the modern unibody chassis design entirely. He would argue for a return to modular, hyper-durable architecture.
Meaning what, practically?
He would demand that machines be engineered with the metallurgical equivalence of self-healing Roman concrete. If a component takes high kinetic stress, it should be over-engineered to withstand 10 times that stress. He demands that consumer technology last a century, requiring only minor, localized upkeep rather than systemic, wildly expensive part replacement. Planned obsolescence is an economic crutch that betrays the core duty of the engineer to build things that actually last.
I mean, nobody likes paying for a total suspension overhaul or buying a new smartphone every 3 years just because the battery is glued inside the casing. I completely understand the frustration there. But over-engineering consumer technology for a century is fundamentally antithetical to technological progress.
How does durability halt progress? A phone that doesn't physically break doesn't stop a software engineer from writing better code for it.
Because hardware permanence traps us in the past. Think about the very first computers. If we applied Apollodorus's mandate to ENIAC or the early mainframes, if we demanded that they be built out of indestructible materials designed to last 1,000 years, we would still be using vacuum tubes today.
I think you are conflating the iteration of the processor logic with the physical durability of the housing.
They are deeply intertwined in consumer tech. Form follows function, and function evolves rapidly. Planned obsolescence, as flawed and frustrating as it is for the consumer, creates a mandatory economic cycle of rapid iteration.
A cycle of waste.
The revenue from the disposable, temporary machine is what funds the immense research and development required for the next generational leap in technology. A hyper-durable, century-lasting electric vehicle sounds wonderful, until 10 years later when battery technology leaps forward by an order of magnitude. Suddenly, your indestructible Roman chassis is too heavy and rigid to accommodate the new power cell. Modern engineering rightfully prioritizes agility, abstract complexity, and iteration over rigid permanence. We build things to be replaced because we firmly believe the future will invent something better.
And yet, in our pursuit of that speculative, ever-improving future, we just fill landfills with synthetic plastic. We burn out our massive server farms managing bloated asynchronous polling requests. We build billion-dollar corporate ventures on foundations of sand that collapse the very moment interest rates rise, all while operating disorganized data lakes that literally take entire teams to decipher.
While simultaneously connecting the entire globe, processing millions of encrypted transactions a second via cloud architecture, and creating databases that can instantly adapt to the chaos of human behavior without breaking.
Which brings us perfectly to a place of summary, I think. As we review the archives from the Temporal think tank, my position remains completely steadfast. Ancient mechanics provide a proven, highly critical blueprint for radical modern efficiency.
Right.
By treating data as physical weight with Archimedes, applying absolute geometric grid zoning to our schemas with Hippodamus, demanding the foundational unit economics of Imhotep, and enforcing the monumental durability of Apollodorus and the event-driven mechanical logic of Hero, we can finally strip away the bloated friction of the 21st century.
And to summarize my perspective, while these classical philosophies are brilliant mental frameworks, modern engineering must live in the reality of the modern world. Our environment rightfully prioritizes agility, abstract complexity, and continuous iteration over rigid permanence. A sprawling NoSQL database, an auto-scaling chaotic cloud environment, and even a rapidly iterating consumer hardware market. These are necessary, highly evolved adaptations to a hyper-connected, completely unpredictable landscape. You simply can't build scaffolding out of marble.
Though I suspect we can both agree on one point of profound convergence here. There is immense value for senior architects in viewing abstract software engineering through the lens of physical forces, conceptualizing a CDN as a physical lever or network traffic as a hydraulic flow. It gives us a concrete vocabulary to identify inefficiencies that we might otherwise just ignore as standard industry practice.
Oh, absolutely. Understanding the indestructible foundations of the past provides vital perspective. The mental model of leverage, of physical mechanics, of load balancing, it grounds the abstract, invisible code into a physical reality. If you're an engineer asking yourself, would Hero of Alexandria consider this API endpoint mechanically sound, is a masterful way to stress test your own systems.
I highly encourage all the developers, architects, and founders listening to explore the archive blueprints in decoding the pillars of history for themselves. There is so much more to unpack regarding how the logic that governed ancient stone perfectly translates to modern silicon.
Yeah, it really forces you to look at your own tech stack and ask, is this system actually necessary, or is it just what we are used to deploying?
And we will leave the ultimate conclusion up to you, the listener. Because at the end of the day, when you look at the architecture of your own digital deployments, you have to decide, are you just taping together flexible scaffolding to survive the next sprint, or are you engineering a foundation designed to hold the weight of the world?
Ancient people were master engineers. Subscribe to Ancient Archive Blueprints as we explore more master designs from the past.